This is a really quick overview of what are the current solutions based applications we have. We have mentioned before that cell broadband engine has got its applications in digital video surveillance, it's got its application in aerospace, space and defense sector, financial services and banking applications, also seismic computing, high performance computing, let's see, what am I missing? Electronic design and automation, medical imaging, and digital media and digital content creation. So these are some of the examples of what IBM already has demonstrated workloads, and what are some of these are in progress. Each of these areas are being worked on by a different team in IBM. So there's this first one application which means basically it stands for FAH. It's got some applications in life sciences and biomedical. They have already demonstrated some results based on the Sony PlayStation 3. So imagine just having like a $600 or a $500 to $600 appliance with you and being able to do something really useful beyond beyond just gaming. You might have heard about this very famous deal that we have made with one of the leading US's leading defense organization, Los Alamos National Laboratory. Basically, there's two major defense labs in US. One is the Los Alamos National Laboratory, and the other one is Lawrence Livermore, right? So we have signed the deal with Los Alamos, and the final goal by 2009 or 10 is to produce 1 petaflop of performance. So 1.6 petaflop peak double precision performance, floating point performance. So it's basically a hybrid environment where cell broadband engine is used, as this diagram shows, can be used as a Linux cluster with 8,000 plus blades. So that will be 8,000 times 16 SPEs. So immense power. And the AMD Opteron system is used as the master cluster. So the reason we have to club up with AMD is because the main bottleneck on the cell broadband engine, which we cannot avoid, is basically the PowerPC, right? It's not really powerful. It's just a puppet master, which basically just runs the initiacy application and tries to offload work. It just pulls the right threads. So AMD Opteron processor was proven to be much more better, and for this particular application, it was cell broadband engine is used more like an accelerator. Okay. There's finite element solvers and computational fluid dynamics. There's some workloads already implemented in the area of fluid dynamics on cell. This is in process. We don't have I don't think the FM is available in market today, but this is something that we are working on. There is some smaller workloads, not a full end-to-end solution proven yet, but we have for large objects, as it says, we have demonstrated a performance of 52 gigaflops using 8 SPUs. And there is a website at the bottom. This is we are working with a company called Digital Medics in Germany. So this website will give you more details. DVS, this is another major play with a few $1 billion revenue potential for IBM. So basically now in the airports or in major, say, stores, how are the security cameras there? There may be like 10, 12 or maybe 5, 6 only security cameras in different areas, and all the data that's captured from this camera is stored in these many disks. And by the time you look at the disk, you rewind and find out, then there's a person sitting manually in the office reading each of these disks and trying to see if there was any activity. So naturally, the productivity of the human eye decreases after watching so many tapes back to back. So with cell, what we're proposing is all these different things that can be done: object detection, 2D object tracking, classification, multi-scale tracking, multi-camera handoff, face cataloging, metadata representation. Basically, how the cell broadband engine will be basically used for this thing, the video compression and analysis phase. So with cell broadband engine, there can be maybe like 50 or 100 cameras in different, or maybe more than that actually. I don't know the current numbers yet, but they'll be there all in the airport, and real time they'll be reading in this video input from the camera, compressing it, analyzing it, and sending in via the surveillance middleware and via this external terminal, it will send an alert. So in other words, within a minute you will be knowing that okay, there was some suspicious activity and it will raise an alarm, versus maybe the thing already goes off, or bomb already goes off, and then you try to go do recovery. But instead with the cell broadband engine, with the cell processors and this current model with the right middleware and the end user equipment, we can actually do real time alerts and do a lot of do a lot more than what's being currently happening in the industry. You can do things like show all the cars that drove north on 10th Avenue. To if you want to go ahead and to backtrace the activity, you can see that okay, beyond this certain line there's a trip line. Beyond a certain line in this parking lot, show me all the cars with this particular with the license plate from Texas or something like that. So a lot of neat things can be done. There's a website for IBM. This is based on the IBM Smart Surveillance System, which was basically a people vision project from IBM Research Labs. Very well recognized. There was recently a really nice news article also about this. It's getting worldwide recognition. So there's detailed descriptions available on the IBM Research website. I'm thinking it's not internal, it is an external website. If you need to know more, please do let us know. There's more details about what the Marvel system is. It's called Marvel, the Smart Surveillance Engine. So this is basically modeling of data and producing high resolution 3D graphics images, reading the data. And now the most outputs that we have is all two-dimensional. The whole world is progressing towards 3D outputs, right? 3D graphical display, high dimension data. So this is another, I+ is another solution area that we're currently working on, where you can observe this input, model it, and basically reproduce it on the computer in a three-dimensional manner. And again, there are some more numbers about if you are from a banking sector, if you're working on applications in the banking sector. Again, we've already produced workloads in the Monte Carlo simulation. There's a team in Germany that did really good work on this. So we have some benchmark results available on that algorithm. Again, the way the cell processor deals with random number generators, random number generators are a big part in when it comes to any play in financial sector. So again, cell processor is very good for that. And here there are some results over here, over 8 cores versus 16 cores, and the peak gigaflow performance for FSS-based solutions. This is the company, we have already talked about this, RapidMind joined hands with Real-Time Technologies. RTT is also a Europe-based company to produce something called DeltaGen. RTT has got something called DeltaGen, which basically does complex 3D visualization for cars, really upscale cars. I don't know if they're doing something else for like shoes and things, but I think mostly it's for cars, automotive, aerospace, and consumer goods sector. So yes, consumer goods also. And they did demonstrate a really nice application for the SIGGRAPH conference last year in 2006. Accelerator, this is just explaining the accelerator hierarchy for DCC, digital content creation. Basically, this is just demonstrating that how cell broadband engine, when used as an accelerator, there will be obviously an encoding device, a video capture device, and how getting that data from the device, moving the computational part of it over to the cell broadband engine can be just achieve excellent results when it comes to 3D visualization. It's basically just the device that's doing the data capture of it. And then over here, I wish we had an image of a real blade center. I think we did have in one of the day one presentations that Duke had gone over. But this is what you would buy from IBM. So you would buy this, and then 7 of these blades go into 2U slots. Right now it's a 2U slot. Next year we're going to make it a 1U slot. So in one blade center chassis, it's roughly the size. It's very portable. Basically, it's just this high. And you can have 7 blade centers plugged modular wise. So the chassis itself has got the I/O connectors, network connectors, everything else. And there's a management module that you can open up, and you can very neatly configure, find out how many blades are there, what are the resources available, how do you configure the network, give them all different network IPs. But this one thing has got 2 cell processors and 16 SPUs, and it just looks just this thin enclosure, which has this cell processor. Again, with more details on how you do the rendering of the data from here, move it over here for the data management part, storing and doing something else which does not involve really high level computation. When it comes to the computation, move it over to the cell blades to produce the to do the analysis and compression. And basically, I think this device, this thing, it looks like a system I or P or some kind of that kind of server, or an HP server or something. So it will basically read all this input data, put it in frames, and this is basically the device which will be sending the cell broadband engine all the frames, frame by frame, to process. Okay. Again, more details on remote visualization, and this is basically something terrain rendering engine. I think we have a demo. I will show that demo in order to explain this further. Basically, there is because with this high satellite imagery, recently there has been a lot of progress in satellite imagery, right? So you have all these satellite images of terrain. So what the cell broadband engine can do is capture the data, and then on the blade it will basically do its server side rendering, and to produce the output, and basically to produce it over this monitor, it would do it employs some a technique called raycasting. So it will try to determine the depth, combine it with the colors that get reflected from the surfaces to produce the final image. And this is just showing the advent of processing, how we have been going on a steep, on a high slope, and just making significant advances when it comes to information processing. Started with the mainframe batch, right? Batch processing was the coolest thing back in 70s, and then moved over to mainframes, and then a mini computer, multitasking, and then the Linux introduced the concept of multitasking, and then the whole world with the 2000, the dot-com boost, everybody moved over to the internet, and now the revolutionary concept is cell broadband engine, or so we say. Okay, so developing an ecosystem around the cell BE. Our mission is to develop programs, be it programmability tools, be it a scheduler, be it a debugger, be it a IDE development kit, anything that can help the programming community and make the programming a few steps easier. And also fill up the solution stack. If there is an application in, say, imaging, right, there are a few core algorithms that are needed in the imaging area, and there are a few what you might call plugins or encoders or decoders, be it anything. So in every solution area, we want to complete the solution stack. So by that way, we're trying to build the cell broadband engine ecosystem. Again, tools must address the creation of new code. In any tools that we need, they have to address the porting of existing code, portability tools, demos, proof of concept, of proof of technology. That's another thing that we do for different workloads. In other words, if I want to see if Black-Scholes algorithms, or let's pick up a Euler integration formula, for example, is it a good fit for cell or not? So in order to determine that, we do something called a proof of concept. We port it over to cell, and then we try to get the performance numbers and benchmarks. And it becomes a benchmark when we're actually comparing it apples to apples with another architecture which is equally compliant, either a equivalent G5 or Intel a dual core processor or something like that. So we do a lot of POCs and proof of technologies. So what is the strategy? Provide development training. We did our part, step one, and leverage the academic interest. So if there is any interest from the academic community, produce demos and papers. That is the key to all technologies. Have as many papers as possible, right? Verify the performance potential of cell BE. So in other words, if there is an application which you think is a good fit, right, verify that, or yes it is, and then see if we can get the results out. Produce libraries, example code. Make sure that everybody gets a chance to play with the development kit. And then target ISVs in markets. So the more assets we have, the better presence we have. So it's very important for any technology to be able to survive, to have ISV presence, academic interest, and open source assets in the community. So we do have lots of university programs that we do, some high-touch universities that we work with. So high touch programs and medium touch programs and low touch. For medium touch, we have something called well, actually, let me go one by one. For the high touch universities, we have one focal point that works with every university. We give out loaner systems to the universities. Again, this is all. We're not saying that we do that with every university. This depends upon what kind of collaborative research we can do with the university. We definitely give remote access. In other words, we have some QS20 blades available in what is called a virtual loaner program. So if you have an application that you have developed and you want to really run it on the real hardware, send us an email. We will try to get you an account with something called Partner World, and then get you set up with remote access so you can directly log into the cell blade and develop and benchmark your application. We have something called SIR grants and faculty awards, and of course we provide training worldwide, and Duke is the lead for worldwide training, does an excellent job, already has conducted workshops in numerous places in China, Shanghai, Beijing, Taiwan, Singapore, Malaysia, Brazil, all over Europe. So anytime you have any training suggestions or any additional venues, please do let Duke know. Medium touch universities, we provide VLP support, virtual loaner program, where students can remote log into the hardware. We have forums where anyone can post a question, and there are developers actively monitoring the forum, and they'll let them know. The forum is a really healthy community. You can see all kinds of really nice technical questions and discussions going on any subject, be it A&D, be it financial sector, be it anything, and lots of really low level technical question too. I'm trying to do this DMA operation, it's not working. You can ask your DMA list question if what we provided was not satisfactory enough. Any question that you have that you're not satisfied with, and a bulb goes on and you're like, oh, how does this work? Just go ahead and post it in the forum, and somebody will respond to you. If they don't, please do write to us and let us know. There's a low touch approach also, where we provide online education. Duke has set up this online IBM education system, which is called IBM Education Assistant. So there is a website link. I think it was there in the initial programming slides. You have it on your CD. And also you can purchase equipment. So if you have something and if you're trying to build a cluster, if you're trying to do something for university and you want to purchase a blade, please do let us know. So sample of events, they recently did the 1-day workshop at Georgia Tech in Columbia University, 2-day workshop at Minnesota, again worldwide workshops everywhere. We have this university challenge, which is getting a lot of recognition. We already have in 1 month over 30,000 hits. Third-party development tools. We are working with a number of third parties. So in our continuous effort to make cell programming easier, we are working with a number of tools, ISVs, to provide programmability tools. So if you don't want to do the DMA, don't want to worry about all the task splitting and everything, we are working with better programming models, vendors that are providing better interfaces to make it easier for you, provide more abstraction level, so you don't have to worry about so many low-lying details. So we are working during the course of this year, and next year we will have a lot more tools that we can talk of and showcase around this technology. Some of these are in the pipeline. A lot of BLAST libraries are, MAS library, FFTs, FFTW. We already have support for MPI, OpenMPI, several multi-core frameworks available. Mercury Computer Systems has produced quite a few programmability tools, something called TATL, something called multi-core framework, which basically abstracts the responsibility from your hands to do any kinds of memory, data streaming or data partitioning or DMA operations. So in other words, you don't have to worry about synchronization and memory management. Continuously working on debuggers and performance analysis tools. We also have play in embedded systems. So in other words, we are working with a vendor, Mentor Graphics, for developing a real-time OS around cell. So in other words, we are targeting from the smallest level that starts with embedded computing, embedded systems, and therefore we need some real-time OS support, all the way till the most high-performing clusters, to hybrid programming environments. This is a good example where Cell SDK is a starting point. Then we have something called the Block Management Library. This is developed by one of our colleagues at IBM that works with me and Duke. He has produced this library. We are releasing it into open source. Basically, this Again, another abstraction layer. It takes away the responsibility from your hand to split the data buffers up and do memory management like DMAs and all. So you can use it. It's a very user-friendly, high-level API that you can use. We are currently in the phases of getting open source licenses and releasing it in the community, licensing and everything. So once it's if you are interested in BML, do let us know. It's just a high-level API that will abstract the need from you to do the DMAs yourself and synchronization and everything. And with the pipe library, BML is a two-sided data transfer. Pipe is a one-sided data transfer. Both of these came as requirements from the A&D, aerospace and defense sector. We're working with Raytheon, and they needed something that was not available. So this proved very useful for their requirements. That's also another framework which abstracts responsibility from your hands to do synchronization. Again, there is documents and documentation available about all of these in the SDK, and if you don't find any documentation, do let us know. Another thing called ALF, it has got a similar use as BML, just a more low level. Again, Mercury tools are available. Today and RapidMind are complete abstraction. So here, by going on this is like a line. Starts from the low-level tools, low-level, high-level, high-level, and this is complete abstraction. Today and RapidMind, what they provide, the environment, you don't even need to know how to vectorize. You don't need to know how to split the task up, nothing. You just do your scalar program, take your scalar program, convert the data types, build it with your favorite compiler, and that's it. Okay, IDL cell applications. So right now, this is the best I guess we have. We don't have a list of projects right now, but we'll certainly follow up with you. So target areas, obviously digital media, image processing, video processing, any applications, algorithms that fall under these categories are an extremely good fit. And if you see, DSP is one of them over here. All right, and also graphics, floating point intensive applications. Pattern matching, this year, this is not our highest priority, but still it is an area where we have already identified over 4x of performance benefit. So we will cover programming tips and techniques really quick, some porting methodologies, and then move over to SPU overlays, another effective technique, because the main challenge, a big question that is there in everybody's minds is that I will definitely have more than 256 kilobytes of code and data. What do I do? So Duke will cover that. There's also a very good paper. Dan Brokenshire is another senior technical staff member in IBM. He has written a paper in DeveloperWorks, 25 techniques to exploit the cell broadband engine. It's a very neat article. So if you can go to DeveloperWorks and search for papers, articles, proof points that we've already developed. You'll find a lot of neat material. There's no dearth of material on anything in IBM. So we've covered the strong points. Obviously, by now everybody knows that yes, it's 8 plus 1 is the magic number, and actually it's 8 plus 2. These SIMD engines are decoupled. That's another key thing. There is a very simple architecture, no complex hardware-based features available. Decoupled SIMD engines. Obviously, the PPU is two-way multi-threaded. The chip area is very small, and that makes the power consumption brings the power consumption very small. Not the chip area, but the simplifications that we have done in the hardware. That is by separating the PPU and the SPUs, and by the memory architecture. All those things add up for the less power consumption. Because in a way, with the advent of technology, the limitation has not been CPU power anymore. You can go on building deeper and deeper pipelines. The main roadblock now is memory latency, right? Several thousands of cycles in most cases. So that's our key challenge, and that's what we're trying to address with this technology. As my performance goes up, my power needs to be low. So 128 registers, local store. The DMA bandwidth is 25.6 gigabytes per second, 16-way SIMD fashion, fully coherent buses and memory. Peak bandwidth for EIB is 204.8 gigabytes per second. Programming tips. So we now know that the level of programming is not the most high level, right? It's not Java. So there is certain intelligence and awareness of hardware that's needed. Not hardware as such, but the hardware features that's needed as such. Again, as Duke mentioned, this is a new technology. We are evolving right now. We're working on making more and more tools that are address the area of programmability available commonly to every developer. So dual issue rate, we have dual issue pipelines, have to overlap DMA with computation, designed for limited local store, the code has to be compact. Loop unrolling, again, we have to keep in mind that you cannot keep on just unrolling the loops, right, because it increases the code size. So it's a delicate balance between how many times you want to unroll the loop versus what is the performance benefit that you want to get out of it. Shuffle byte instruction is a very key feature available. Avoid scalar code, because again, when you're using scalar code, what are you using? What is their disadvantage? We're not using all the 128 bits, right? We're not using the full cache lines. So avoid scalar code. And choose the right SIMD strategy, load and store only by quad word. Instruction scheduling, different instructions take different, have different lengths and stalls. For example, single precision have 0 stall, but and the latency is 6 cycles. Integer multiplies is 7 cycles. Double precision is 7 plus 6, so 13 cycle latency. Right now, we're trying to change that. And there is pipe 0, which is the even pipeline, and the pipe 1 is the odd pipeline. All the memory related instructions are there in the pipe 1. So in the SPE, there is a high penalty for branch misses, right? 18 cycles. You can use branch prediction. There is software assisted branch prediction that's available. If it's successful, it will completely avoid the branch penalty altogether. So use software predicted branch prediction, and I think we have an example coming up very soon here. So if you have an if-else loop, normally in today, this is how you would do the if-else loop, right? If A greater than B, C plus equals 1, else C plus equals B, C equal to A plus B. Instead, what we're asking you to do, and this is definitely a branch. If you don't do any kind of branch hints, the branch will happen and it has its own penalty. So we want to save that altogether, right? So what do we do? So we do, first of all, we do a compare greater than A comma B. It will find out if if A is greater or B is greater. The mask or the result is stored in the bit form in select. We do SPU underscore add C comma 1, SPU underscore add A comma B. So in other words, we are in the scalar code or in a normal code, you only do one of the two computations. You either do C plus equals 1 or you do C equal to A plus B. In this case, we're saying do both the computations, right? And leave it on runtime on the select mask. This avoids the branch. And C equals SPU underscore self. So depending upon this mask, the select, it selects if it should take the AB value and store it in C, or if it should take the C1 value and store it in C. Now, one key thing to remember over here is that sometimes it's not as simple as C plus equals 1, right? There's a whole bunch of code in the if loop versus else loop. That's again up to the programmer's decision that, which one, is it safe? Is it worth it to do both the computations? Does it take more cycles to do both the computations versus does it take more cycles to basically just let the branch happen? Unroll the loop, again remember the code size. Every time you unroll the loop, you are saving cycles, but you are also increasing the code size. So do always measure the code size. If you unroll the loop like 8 times and you go back and you compile your code and see, oh god, it's 300K, go back and reduce by a factor. SPU unroll the loops to reduce dependencies, and there are some the transform light workload is already demonstrated. There is a paper out on Developer Works again, which basically demonstrates different workloads and how they were done. If there was a matrix multiplication workload and which showed like the 10x or 12x benefit, how did they get the benefit? They go over the strategies they used. There's papers. There's a paper on FFT both from Mercury and from 3 developers. We showed the pictures also from IBM, which demonstrate, okay, if I did produce the results, how did I do my optimizations, like the approach and all. There is different papers available on different suggested workloads. Again, all this material is already out there. And this is actually some data using the XLC compiler, some demonstrated results for the transform light workload. Again, this is an example of workload which is hardly this small. The code is like hardly 12 lines or 50, no, not 12 lines, maybe 20, 25, 30, less than 50 lines of code. So it's a small workload, but it's a really crucial workload in a lot of areas. But by demonstrating this workload and putting huge amounts of data on the workload, you can pick up a sizable program and demonstrate that yes, by optimizing and doing techniques like this, you're seeing a result in performance. Function inlining is another thing. If there is a function that you can inline we highly recommend you to inline it. It eliminates the two branches associated with function call linkage. The first one is branch and set link, right, to store the address where it's going off from, and then branch indirect for the function call return. So, but then over aggressive use of inlining can result in code that reduces the local, that will consume a lot of local store space. So do think the techniques like software pipelining, this is just a general concept, not really particular to cell programming. A lot of times we try to enforce pipelining where we are trying to do two things in one loop. The way you will write the code is basically just like double buffering. So while you're doing this part, you're also doing a second part of the computation at the same time. Avoid integer multiplies. SPU only has 16-bit integer multiply support. So if you wanted to do a 32-bit multiply, you will need 5 instructions, right? Like 3 adds and 3 multiplies and 2 adds, something like that. So avoid 32-bit multiplies. That's another thing if you can. Keep the array element size to a power of 2. Cast. Okay, so basically, and in order to keep it to a 16-bit multiply, try to do operands, cast it to unsigned short before you do the multiplying. And because SPU only supports quad word loads and stores, and it always does the loads and stores on 16-byte boundaries, so try to avoid scalar code. The SPU code should always be vectors, vectors, and vectors. Only if it's absolutely required, if it's a counter for loop or something, is when you should use scalar variables. There's instructions available to switch from scalar to vector and back, to pick up, to store locations in particular areas on the vector, or to extract values out of a vector. Choose a SIMD strategy appropriate for your algorithm. Evaluate array of structure organization. Basically, if you want to store all x values in one vector, or you want to store x, y, z, w values. So it's your trade-off. It's your choice as to what is appropriate. It's actually not your choice. It's the algorithm's choice as to what is a better strategy. So to make all these design decisions early on and spend a lot of time doing this, making these decisions, it will really yield a good result. And this is another example. Basically, it's just taking an example of what kind of results you would expect for if you did a vector across computation versus a parallel array versus parallel array for one subdivision point at a time for 4 independent triangles versus 4 subdivision vertices at a time for a single triangle. So it's just another demonstrated workload. There's more documentation also available for this on the web. And again, there's different strategies for partitioning and work allocation. There is something called, I think we have the next slide that covers that, the porting techniques, where your programming model can vary. It can be, actually Duke already covered all the programming models, the PPE centric versus SPE centric, the master and slave kind of configuration, the fork and join kind of computation. The FFTs largely use fork and join, right? Because it's numerous small computation, and you try to break it up into the simplest phase, and at the end you combine the results from all these computations into one result. Offload as much work onto the SPEs as possible. Accommodate potential data type differences. Just examine your data and see if you really need 64-bit, doubles or floats versus 32-bit versus 16-bit integer multiplies. Exploit the SIMD. Write your code so that there is no false dependencies. Let the compilers do the auto SIMDization. If there is false dependencies in your code, the compiler's hands are tied. Write assembly. If you are an assembly person, write assembly. Programmer specified user generic. So there's all these features available: the branch hints, the inline function inlining, loop unrolling. All there's techniques available. So it's quite interesting to deploy all these techniques and see the difference it can make in your code performance. Use SPUlets for quick prototyping. Say, for example, you just want to know, okay, I just want to see if SPUs can do this computation fast enough for me. I have very high expectations, right? You don't want to deal with compiling your program on the PPU, send the data all to the PPU, onto the SPU. You just want to compute on a small bunch of data, right? And then see if, or maybe you just want to split it up, the whole data up already into the SPUs and see if it's fast enough. The vectorizing part of it, right? You can do something like SPUlet, which is a standalone program, right? You just so the data is already there in the SPU main program. You don't have to do the sending and everything. So that will give you a quick overview. Okay, is this fast enough for me? Is the vectorizing and the optimizing part enough? Then if it's good enough, then you can add the DMA part and everything else. There's software cache handling applications, basically the software managed cache. The source is available in this directory. Documentation is available in this directory. And then there's examples also. So we're giving you everything, documentation, the source code, everything, and test programs that demonstrate the effectiveness of it. So several levels of parallelization available on the cell processor. Now this is a presentation that deals with a step-to-step approach to porting an application. Some real-world examples of what problem we had in hand and how did we actually tackle it. So SIMD processing. So several levels of parallelization available. One is SIMD processing. So we have the ability to vectorize our code. Dual issue is there. So in other words, we can make sure that we're not executing only one instruction at a time. We are executing more than 2 instructions at a time, basically. Multi-threading support available. Multiple execution units with heterogeneous architecture, right? And then we have shared memory multiprocessing, and then distributed memory multiprocessing. This is the cluster kind of configuration where you can couple a lot of, not couple, but you can use cell broadband engines in a cluster kind of configuration. The EIB gives the support. The high bandwidth bus enables us to do that. So basic steps for parallelizing my program. First of all, what do we need to do when we have an application in hand? We have to try to find out if there is concurrency, right? If there is no concurrency, then basically it's really hard to parallelize. If the whole program is serial, there's serial flow of data. So the key points are, what is the data flow? How is the data coming in? And how is the data getting out? Dependencies, right? We have to observe, find out dependency. If there's any concurrency of data. In other words, if the same loop, if there is one section of data that's repeatedly operating on a big bunch of data, several millions of times. So we have to, if there is still some room for concurrency, but the application is written in a very serial manner, try to structure the application so that it does, so that concurrency is either increased or you have means of exploiting the concurrency. Tune for performance. Challenges, data dependencies. Try to reduce the data dependencies. Overhead and synchronizing. Try to reduce the synchronization that you really have to do. The less synchronization you do, the more time you save. So in other words, if everything is fast, the memory transfer is fast, you're doing double buffering, you're probably using DMA list, you're vectorizing the code. But then in order to synchronize one task with the other task and in the other SPs, you're doing a lot of back and forth DMA messages, mailbox messages and synchronization variables. It will negate the effect that you're getting out of everything else or neutralize it. So be careful. So watch out for that is the message. And when you're partitioning work, make sure that you do at least some kind of initial decision about load balancing. And there's obviously, if you're migrating from another platform, there's differences in bandwidth of buses, topology. So observe all those differences and plan accordingly. So locating the concurrency, right? The first step. Analyze the program and its algorithms and data structures, right? What is the effect of overhead of synchronizing? How much synchronization do you really need? Is there any way you can override these dependencies? Identify the program hotspots. There is a very cool, I don't know, have you ever used GProf, GNU-Prof? So it's a very neat profiling tool. Once you run that profiling tool, it gives you an output. It will give you a total number of loops that are there, total number of time taken on all the functions. It produces a flat file with all these different parameters. You look at the parameters, you're like, oh yeah, so this is the code that is being entered maybe 100 times or 1000 times. So this is the part that I really need to optimize. The rest of it I don't need to care. This is the high traffic part. So tools like that are available to help figure out what are the hotspots in the scalar code. So do all processor elements update shared data? Is there any shared data? The shared memory usage in their data. Does one task need another task's data? Are there any race conditions where the data might be read before the other process wrote it back? Is there too much synchronization overhead? Are the interactions among tasks synchronous or asynchronous? So, and then the processing advantages, are they worth the data communication cost? So, observe all these things to locate concurrency, and then structure the application to exploit the concurrency. There are several considerations, right? Task or service level parallelism, data partitioning, task grouping. How can you group the tasks together? Divide and conquer, right? Divide it into several tasks and see if you can and assuming that there is less dependencies between these tasks, it can be a very effective end result. So it could be a master slave, it could be a fork and join. So considerations for distributing application workload and data, processing load distribution, the program structure, data flow, data access patterns, observe all these things. And I'm sure there's lots of open source tools available to help achieve these results so that we don't have to look at the code, hundreds and hundreds of lines of code. And it's impossible to look at 10,000 or a few million lines of code and say, okay, where are my hotspots, right? It's very hard to do, it's unrealistic. So there are tools available that will do it for you. There's again different application partitioning can be basically PPE centric, where the main application resides in the PPE, and it will either stage it in a pipeline, like you do this part and you do that part and you do this part, versus parallel stages. So like pipeline is one below the other, so it splits. It has one task and it spawns up 3 threads that are working at the same time, versus parallel stages where there's dependencies with the first stage for the second stage. First SP create thread finishes, and then the next SP create thread can be started off. Steps for parallelizing a program. First, understand the program, choose the programming tools and technology, high level parallelization strategy, low level parallelization strategy, and then design the data structure, iterate and refine, fine tune. So we have this video, right? Basically this is about surveillance of video. So we have a video, right, and we are monitoring this. There's techniques called segmentation and background subtraction by which you can detect activity. So in other words, the video looks like this. You try to build this background over a period of time so that you can find the differences. How do you monitor activity? How do we monitor change in the activity? The only way we can do that is to find out the differences between the foreground and the background, right? So there is this background frame that gets built over a period of time. And via segmentation, what you can do is to detect the foreground objects and differentiate them with the background image. So the end result would be something like this. There was probably something over here. I don't know why she's cut off like this. Now the complexity, right? There's several complexity with this. In general, in real world, when there's all the security cameras on top of all these buildings, right? There's moving rainbows at sharp edges. It's called the NTSA effect or something. Then you have to adjust for weather changes. There might be wind. There might be very low visibility, fog and rain. So the camera has to adjust for all this, and the data analysis has to, not the camera, but the data analysis has to adjust for all this. In other words, even if there is rain, there has to be some mechanism by which you can still analyze the data. Handling swaying of cameras, if the camera just moves off, how to make sure that the software is capable of that, of detecting that and reanalyzing the images. And doing things like auto gain control. I don't know what auto gain control is. And then auto white balance. So basically, in this BGS application, which is BGS stands for background subtraction, you can build a background model over time, and then in image processing, or in general in imaging, there's nothing called an empty frame, right? There's no scene is empty. It's always a mixture of some kind of pixels, be it grayscale or 8-bit color or grayscale. So tracking the illumination changes and adjusting to it accordingly. There was all these stages in a full-fledged application. So this is via input image, and you could do Kalman smoothing to it. You clean it up, do motion edge energy, process it for shadow and highlights, texture, find out the texture differences, pixel differences, and again all these processing that you could do, quiescent area addition, slow update blending. I don't know all of this, but some parts of it, yes, I have worked on. Stationary healing, and then we get our background, right? So there's all these stages that go into, and even when the final, or the almost final stage comes out, you still have to do the statistical thresholding, some contour smoothing to smoothen in the edges, and then component pruning. Finally come out with a mask. There's some algorithms and there's detailed information available. If you are interested in this particular workload, we can provide you some documentation. So now, our phase was to do that video analysis, compression and analysis part, right? So if we have to do the image pre-processing part and the salience detection part and the mask generation, and then at the same time do model maintenance, and then that gives us the final objects. Now we have, at that time there were many, so our design choices, right? We have this full application with a few hundred thousands of lines of code, many functions involved, right? And then functions tend to access multiple frames. Every single function needs some access to some kind of frames at different times. And then some frames contain color images. It becomes much more complicated because it's not just dealing with 0 through 255 pixels anymore, but we're talking about 8-bit color, maybe more, 16-bit. And then the original code was written in C++, and then processing one frame touches 4 to 6 megabytes of data, just one frame. So we had three alternatives, right? Complete the BGS, the background subtraction in a single SPE for one video stream. So take one stream and then finish it in one SPE. Or we can organize it into groups with one group per SPE, or we could do individual BGS function partitioned across multiple SPEs. So what did we finally do? These are the alternatives. So take one video stream and give it to one SPE. In this case, we needed code overlay because we're trying to give the entire processing responsibility to one SPE at a time. This is when we used code overlays, which Duke will cover in the next session, and it made some difference. And so the other option was to make it as a pipeline. This didn't work very well because load balancing comes in. Some phases might take longer than the other phase. Third one, we could data partitioning across SPEs. In this particular application, it was not so easy because there were lots of dependencies, there were lots of functions, and all these functions were accessing all these frames at different times. So this we could not do. So we considered all these design considerations and went with the first alternative. So this is what we finally did. Data partitioning was not feasible for all functions, so all images stored accesses from main memory. Code partitioning criteria, right? Code size and the compute time are the two key criterion to find out, the code partitioning strategy. So we figured out there is 4 compute intensive pieces, right? Plus the coordinator. So each module ranges from 180 kilobytes to 240 kilobytes with code and the temporary buffers that we had used. And this was the final application, the way the process that we came out with. First of all, allocate the data block in system memory, right? Obviously, you have to bring it up to into the RAM, and then pass the address of the data block to the SPE function. The pre-process stage. For the third stage, the SPE initiates the DMA to transfer data to local storage. The fourth one, SPE initiates the DMA to start transfer results back, MFC get input, and then the SPE notifies PPE of the job completion. So this was the rough structure, and this is one critical application that IBM has a big play in with some surveillance-based, airports and stores and everything. Again, another example is image compositing. Base image, we have the base image B. This is overlay image A, and then we want to come out with this resultant image. So these are for all the images, there's an RGB and alpha value. So this was the formula that was supposed to be applied to all these pixels, all the RGB and A values, the alpha values. So this was to be done for these several hundreds of thousands of pixels. And so this is how we did the data flow for it. The other was read A and B, right? So read the image A and B. Like if you go back to this image, right, we have the base image B and then the overlay image, right? So read both the images and try to do the formula, but do it such that you can overlap different stages and form like a pipeline. It's just a basic pipeline. It's just that we're trying to enforce the pipelining concept into our code right here. So while we're doing A equals A by B, and then you write it to A, right? And then you write the A image back to main memory. At the same time, we try to do the next two blocks from the image A and B. And then while you're doing the write, you're trying to do the compute, which is on the next 2 blocks, you're doing A equals A by B. And at the same time, you're trying to do another DMA operation initiation, right? So this is how we bring out some good performance out of some applications. And these are the performance results for 120 images, A over B, 120 images per second for 4 SPEs, and there's some more numbers for more images also. Okay? So multi-buffering helps. Now remember, you do have VMware, but I strongly recommend that if you have an x86 PC, right, try to partition it, create a Linux. If you're not a Linux person, it's high time. Switch to Linux. So create a Linux partition. There's several partitioning tools available. Create a Linux partition and install SDK 2.0 in a native environment. VMware is good. It gets your feet wet. It gets you up to speed real quick. But when you want to do real applications, real workloads, it's slow. And you will realize that you can't even open up a browser and check your email because it takes forever to come up. VMware takes all your memory. So, really, if you want to just get down and you're developing a real workload, please do it natively. Okay, too much overhead in creating threads, so the lesser threads you create, the better. Okay, that's it.